Hello friends, the topic for today's discussion is attributes of graphics primitives. So coming to the list of contents, we have introduction, color and grayscale, line attributes, and many more to discuss. Coming to the introduction, what is attributes of graphic primitives? So we will be discussing the basic properties of graphic primitives such as lines, polygons, and the curves which are used to draw basic images. Coming to our first topic, we have color display in monitors. So how color is displayed in monitors, we are going to discuss that. So there is a concept of frame buffers that are used in order to display color. So there are three primary colors, that is red, green, and blue. In the combination of these three, we vary the intensities of red. We will balance the intensities of red, green, and blue in such a way that we get a distinguished color. So the number of colors mainly depends on the number of bits that is allocated to each of these three primary colors. For example, if we allocate 8 bits of video memory to the color display, we can get a variety of 256 colors. So it's a palette of 256 colors where we can select any color, and it's the highest number of colors that can be displayed, distinct number of colors that can be displayed on the screen. So the color display basically follows the additive model. Coming to the color depth, we have 2 bits allocated since it's only black and white, so we are having only 2 bits. So if it's a combination of 8 bits, we will get varying intensities of 256 varying color intensities, that is of black and white. So these were mainly used in olden times, the graphical displays. Like I said, if you allocate 8-bit color, 8 bits of memory to the color for displaying colors on our monitor, so we would get a number of 2 bar 8, because when it comes to the machine level, binary bits are stored on 8-bit color table. So it's a combination of zeros and ones, 8-bit strings. So it's 2 bar 8 comes to 256. So in that way, each pixel is represented with an 8-bit string when it comes to the machine level or the binary level. Coming to the 24-bit color table, it's the same as 8-bit, but the more number of bits are allocated uh, to the memory, or for displaying colors. So we get a larger variety. It's almost around 16 million colors. So the human eye has the ability of distinguishing or discriminating up to 10 million colors. So 16 million is really a good number, so that we can use them for making different images. Moving on to the next topic, that is grayscale. It's one of the important topics apart from color. How grayscale, during when color didn't come onto our monitors, only grayscale or black and white monitors were used. So grayscale is a topic where you use only two colors, that is black and white. So the black and white intensities vary, and they depend upon a uh, uh, different modes. So if you allocate, that is zeros and ones, so there are only two colors here, that is black and white. So the transition from black to white, that is all zeros represent black and all ones represent totally white. So the transition from the bits, the number of string combinations that you get from black to white, is the varying grayscale intensities. So if you allocate a 3-bit length string for grayscale, you can get 8 varying intensities. If you allocate 8-bit 8 bits for only black and white, you can get 256 grayscale intensities. So this is mainly used for black and white images, or for black and white effects. It is being used in mobile applications a lot today. So like I said, the grayscale intensities can be varied, and it depends on the various frequencies in the electromagnetic spectrum. Moving on to our next topic, we have how does the eye recognize color? So the eye recognizes color based on the iris and the light, the image that comes through the pupil and that's formed on the retina. So it's formed inverted. That in turn is processed through the optic nerve, which is sent to the brain and then it sets right. So that's how we perceive and that's how our perception works for images. So considering an apple, we have an apple. So the color, the wavelength that it's the material of which an apple is made. So it's being reflecting red color. So that is why we draw a conclusion that an apple is red. So the retina, the eye's anatomy consists a lot of cone cells, rod cells, a lot of types, uh, which helps us in identifying, which helps us in being sensitive to the color. So there are approximately 6 million cones in each eye that transmit higher levels of light intensity. So in this way, the cone cells and rod cells are used in order to understand and distinguish between colors. Coming to dynamic range is a way in which the human eye just adjusts its levels in case of low lighting or high lighting, or it's just a concept where the image which is formed is based on the light exposure levels. So uh, there are a lot of dynamic ranges which are used in common devices such as LCDs, negative film, and the human eye. So it's just how the eye adjusts automatically to the different levels of light. When it is darker, it goes on a little bit high, like the size of pupil increases, and then when the lights are too high, the pupil size shrinks. So in this way, the dynamic range works. That same concept has been simulated in some of the common devices such as LCDs, negative films, human eye. So the contrast ratio, that is 700 is to 1 of LCDs, is a really good one. But when it comes to a high-end DSLR camera, it's around 28,500 is to 1, which is a really good ratio. It's more than the human eye. So it's got a really good adjustment level, a very good dynamic range. So that is the very reason that it gets on with high quality images. Coming to our next topic, which is an important one, line attributes. Line attributes are mainly of three types, that is color, width, and style. So coming to color, it depends completely on your memory, how much memory you're allocating for colors. If it's 8-bit, you get a variety of 256 colors where you can go on with 256 different lines of different color. When it comes to width, width is basically the thickness of the line. So you can use some simple programming languages such as OpenGL, call some methods such as set width line, where you can define the width of the line. By default, the width would be 1 pixel. So what the computer does is when you set the thickness to 2, it draws a line parallel to the first line, taking it as a reference, and then it draws it parallel with zero distance so that it looks like the line has been thickened. So in this way, we can add thickness of the line. So basically, line drawing algorithms are using Bresenham algorithm for line drawing. So a double width line can be drawn using a parallel line above the original path. Coming to the ending of thick lines, we have three types of joints, that is Milter joint, round joint, and bevel joint. So the Milter joint is where we extend the line boundaries, and the round joint is where we cap the two connections. And coming to the bevel joint, we have a butt cap, which fills the triangular gap. So coming to the line attributes, that is, we should ensure that we should have proper turning for corners. A line cap can be added for ensuring a proper and better appearance of line, where we can use three three types of line caps. That is, the first one is a butt cap where the line segment length is equal to that of a box. When it comes to a round cap, it is rounding off and extending. It's a little bit more than of the line segment length. And when it comes to the round cap, it is really extended, and it's just like a box which encapsulates the line segment. So coming to the next topic, that is pen and brush options. In pen and brush options, we have a pen. Just as we use a pen to draw some images or on a canvas or on a board or on a paper, the computer uses a pixel mask so that it so that it identifies the array of pixel positions. So the computer has given us various options like a circular shape, a rounded rectangle, a line, where it draws the pen. Once you hold your mouse and drag it down, it draws a line on the screen. So there are various options that can be used. So this is the way the pen draws a line, a straight line or a solid line. So coming to the line style, we have three different styles, that is solid line, dotted line, and a dashed line. When it comes to a solid line, there are no gaps between the line spaces. When it comes to a dotted line, it is these dots are printed in a way where the white space between them is more. When it comes to a dashed line, the line spacing factor is reduced, so that the length of the line is greater and the length of the white space is a little bit smaller. So coming to our next topic, it is curve attributes. So curve attributes are similar to those of line attributes with varying colors, dot dash patterns. So the curve, we can say a circular arc is of width 4 is plotted with pixel scan. So raster curves of various widths can be displayed using the method of horizontal or vertical pixel spans. So if the magnitude of the curve slope is less than 1, we plot horizontal spans. Coming to thicker curves, which can be produced by plotting additional pixels. So if we got to thicken the line, so a curve can be drawn. So here in the figure that is given, we have a circular arc of width 4, which is displayed by filling the region between two concentric arcs, which is drawn using a pen or brush. So this is the way a circular arc is drawn with a rectangular pen. So the coordinates are stored, and once we drag our mouse in Paint or any other software, the circular arc is drawn. Coming to filled area primitives. We can use these filled area primitives to fill color in our various shapes that are being drawn. So the two basic approaches that are being followed is one is we start from an interior position, and a point outward from this point is until the boundary condition is reached, which determines the overlap intervals of the scan line. The fill area attributes include the fill style, the fill color, and the fill pattern. So there are three different fill styles, that is solid fill style, hollow fill style, and a pattern fill style. A solid fill style is where the whole color is filled or poured into the polygon. A hollow fill is something, a kind of an empty fill color, whereas a pattern fill is a selected array pattern is used to fill the polygon interior. There is one procedure that is called the soft fill procedure, which provides a new fill color for a region that has a same variation as a previous fill color. The procedures that are used in soft fill procedures, the procedures that are used, application procedures are anti-aliasing and painting packages. So this is the formula that is given for anti-aliasing, that's where T is the transparency factor of having a value between 0 and 1. Coming to the next topic, that is the polygon representation, how the polygon is represented in the coordinate system that is simulated in the computer. We have two-dimensional coordinates here, that's x and y. So that's x1, y1, x2, y2, so on till xn. That depends on the number of sides. So the polygon can be displayed by drawing a line between x1, y1, x2, y2, and a line between x2, y2, x3, y3, and so on. So until the end vertex. So uh, the point is here, the last vertex and the first vertex are joined in order to figure out that the polygon that is being drawn is a closed figure. So we are having various tests that we can perform to decide or that where a particular point that is located, whether it is inside or on the outside. So we have a rule called the odd parity rule to test whether the point is interior or not. So we draw a line starting from a particular point and extending to a distance point outside the coordinate extents of the object and in any direction such that no polygon vertex intersects with the line. So it depends mainly on the number of points of intersection. If it's odd, uh, if the number of intersection points is if the number of intersection points is odd, then the line is said to be outside. Then the point is said to be outside the polygon. If it's even, then it is then the point is an exterior point. Coming to the scanline polygon fill algorithm, we have scanline polygon fill algorithm from its lowermost to topmost vertex, where the scanline taking is taking as a reference point. So the area that is being divided and which comes under the scan line or which comes above the scan line is filled with a particular color. So here we have a picture that represents two scan lines. That is, one is y and y dash. So the scan line y generates an odd number of intersections, as we can see. That is one, and the scan line y dash also represents scanline y dash also represent now even number of intersections that can be paid to identify correctly the interior that can be interior pixel spans. Coming to the vertical scan line for scanline y require additional processing. So the scanline polygon fill algorithm requires the scanline polygon fill algorithm requires vertices for scanline y. They require additional processing. So we can process these non-horizontal edges around the polygon boundary in the order specified, that is either clockwise or counterclockwise. So as we process each edge, we can check to determine whether that edge and the next non-horizontal edge have either monotonically increasing or decreasing endpoint values. So the lower edge can be shortened in order to ensure that only one intersection point is generated for the scan line going to the common vertex. So in this way, the scan line polygon fill algorithm works. Like you can see here, we can determine the edge intersections where yk plus 1 and yk are the coordinates. So in this way, the scan line polygon algorithm works. Coming to the minimum frequency that is used, that is the Nyquist sampling theorem. So this theorem states that the sampling frequency should be at least twice the maximum frequency that is occurring in the object. So if the sampling frequency is less than the twice of the maximum frequency, then we'll have less samples, and that may eventually lead to loss of information. So coming to the next topic, that is pixel supersampling. So what is pixel supersampling? In supersampling, the pixel is divided into subpixels. So there's a further division of subunits. That is, it's 2 cross 2 or 4 cross 4, and the intensity of these subpixels are calculated, and that helps in deciding the overall intensity of that pixel. So each pixel is divided into 2 cross 2 and 4 cross 4. The next topic that we have is pixel intensity distribution. So how the intensity is distributed among pixels. So pixel intensity is proportional to the area of pixel which is covered by the object. And we can see the image that more the pixel area is covered by our object, it will have higher intensity. So they are both proportional. So the more the intensity, or the more the area, the more will be the intensity. So we can say it like that. Coming to filtering techniques, we have been given some filters such as the box filter, cone filter, and the Gaussian filter. When it comes to the box filter, the intensity of the whole pixel is measured equally throughout the box. And the box filter is used in unweighted area sampling, where the filter is not ideal as it will make our image blurred. Coming to the cone filter, we have a pixel which is close to the center weight, and which center weight, which is the weight which is more than the other ones that are further away. And the filter used in weighted area, the filter is used in weighted area sampling. So this is how the cone filter works. Coming to the third filter, that is the Gaussian filter. When it comes to the Gaussian filter, the Gauss function pixel closer to the center will weigh more. So this filter is better than the other two when it comes to filtering techniques. So Gaussian filter is considered superior to the box filter or the cone filter. So we in the example we can see that a Gaussian filter is applied and the edge of the image is more smoother than the one with the box filter. So coming to the weighted pixel distribution. So what is it? The influence on the intensity of a pixel is determined by the weighting function. So the pixel which is right here located at the center, so its intensity is determined by the weighting function. So pixels which are cut through the center will have high intensity and will have more weight than one which is cut along the corner. Coming to pixel phasing, the position of a pixel is shifted by a fraction of a quarter, a 3/4 quarter, or a half of the pixel diameter by the electron beam. So this helps us to point closer to the true path of the object. So it issue removes the issues like staircase effect from our object. Coming to subpixel computation. Subpixels are located near the center of the pixel area that are weighted more. It is more or less used in determining the overall pixel density. And as I said before, these are some of the examples of anti-aliasing images. So the image that is anti-aliased, or the image, so there's a difference. It's a more kind of smoother image which has more clarity. So thank you, friends. Thank you for your time, and thank you for this session. Thank you very much. So the topic we are going to discuss is wireframe methods. So in this model, we represent objects using its edges, or we can say it is represented in its skeletal form. So the wireframe method is, so as the name suggests, representation of the object using its edges and vertices only. So as we can see in our example, the polygon that is there, the barn that is, it's represented using its edges only. So we can also manage the faces of these polygons using this function, where we can assign the parameter that is GL front and back. So where we can GL front and back, where the front side of the polygon or the back side of the polygon can be viewed. Also, we can select whether we want to display our object using vertices only or edges only. For that, we can use the display mode parameter and assign it with the GL point value or the GL line value. So coming to our next topic, that is the character attributes. So if we consider the character as one of the graphic primitives, the properties that would define is its font, its size, its color, its alignment, and its orientation. So what is the different types of fonts that are used? So Times Roman, London Courier, I mean Arial. Microsoft Word uses a lot of a variety of fonts, a large variety of fonts. Apart from that, we have style. We know basically two styles, that's bold and italics. So we can use, apart from that, there are many other styles. Coming to the size, we can adjust the font size of our character by changing its overall dimensions. And the color, like I said before, and I'm saying it now also, the color depends on what variety of colors does the system provide, how much memory is allocated for the colors. So Microsoft Word also provides a large color palette where you can choose, where you can pick one color for your character. Coming to the orientation, orientation is the direction of the character up, vector orientation, or where the string can be set. And coming to alignment, alignment defines how the text should be displayed according to the reference. So this is so in this way, the character height, the character body, and the font size, the base, are defined. The kern, which is representing here, that's near the small j character. So in this way, the different font sizes are represented. The string, any string, can be aligned in three ways. That is the left alignment, the center alignment, and the right alignment. So in this way, the character alignments are there for the horizontal and vertical strings, where we can set the height, that is for around 1 pixel, or we can go width with half pixel, or the spacing can be no spacing to half pixel spacing or 1 point spacing. So text are strings displayed with different character spacing values. So coming to the next topic is anti-aliasing or anti-aliasing. Many of people say that. So for that, we understand. For that, first we have to understand what aliasing is. So it's basically the distortion of information because of low frequency sampling or undersampling. So as we can see this image, because of aliasing, we are having a staircase effect. I mean, there's a kind of figure where we are able to see some steps, which doesn't look good. So we can see this image because of aliasing, because we are having this staircase effect. So to remove this issue, in order to smoothen the image, we use the anti-aliasing effect. So it's nothing but we are resolving the aliasing. So there is the process where you anti-alias, so it's divided into different phases. Coming to the first phase, that is sampling an image. So sampling an image, we know that image sensors provide us with analog signals, but these analog signals are of no use because we can't apply digital processing on it. So the input signal, the analog signal, has to be converted to digital in order to make the computer understand that what information it is passing in. So to convert the analog signal into digital signal, that's what we call it as sampling. Coming to the next slide, we have a pulse code modulation. So that's in short form, its abbreviation is PCM. So which helps us to convert analog signals into digital signals. So basically, we have two processes, that is sampling and quantization. Coming to sampling, it's mapping a continuous function in a discrete one, which is called sampling, and quantization is digitizing the amplitudes. So as we can see in the figure, these are some of the sample points that are being used during quantization, and which has a lot of discrete positions. So the next phase after sampling is reconstructing the digital signal from the sampling. So conversion of digital signal back to analog signal is called reconstruction. So we are converting the digital signal back to the analog signal, and this reconstruction is accomplished by passing signal through an ideal low pass filter. So we can see the image sampling is done through which we get a discrete signal. Now we are converting discrete signal back to analog. So that's what is happening in reconstruction from the samples. So coming to the challenges of sampling, there are various challenges of sampling. So while we perform sampling, we have challenges that occur because we convert analog signal into the digital one, and it may be possible that we are not able to require number of samples, and because that information may get lost, we may get our original signal, our image can get distorted. So if the sampling is not done properly or the reconstruction is done poorly, the image quality or the image that we get is really distorted. Coming to the anti-aliasing and resolution, when aliasing occurs, a high resolution image is displayed in low resolution. So it's the low resolution looks a kind of staircases, and there are a kind of a pixel blurred image. So we know that aliasing occurs when we display high resolution images and low resolution images. So when we try to display a high resolution image, the low resolution device will not have the enough pixels to capture the finer details of a high resolution. So one solution for this problem is high resolution devices, but it is not reasonable because it is going to increase the overall cost of the system. Our next point that we are going to discuss is the staircasing effect due to the low resolution. So because of aliasing, we come across various issues of them, which we call as the staircasing effect. It's commonly known as jaggies. So in this image, what we can see is due to the low resolution, a lot of images being blurred, and that is it is displaying with some staircasing effect. So there are, since it's a problem, so we have some solutions. So one of its solution is to remove this issue by using high resolution devices. But as we know, it's not reasonable. We use grayscale. And in grayscale, we use anti-aliasing slight discoloration, which is added along the edges of the line, causing the jagged edges to blur. We are blurring the jagged edges, so and which melt together, so that smoothens the edge. Coming to the minimum frequency that is used, that is the Nyquist sampling theorem. So this theorem states that the sampling frequency should be at least twice the maximum frequency that is occurring in the object. So if the sampling frequency is less than the twice of the maximum frequency, then we'll have less samples, and that may eventually lead to loss of information. So coming to the next topic, that is pixel supersampling. So what is pixel supersampling? In supersampling, the pixel is divided into subpixels. So there's a further division of subunits. That is, it's 2 cross 2 or 4 cross 4, and the intensity of these subpixels are calculated, and that helps in deciding the overall intensity of that pixel. So each pixel is divided into 2 cross 2 and 4 cross 4. The next topic that we have is pixel intensity distribution. So how the intensity is distributed among pixels. So pixel intensity is proportional to the area of pixel which is covered by the object. And we can see the image that more the pixel area is covered by our object, it will have higher intensity. So they are both proportional. So the more the intensity, or the more the area, the more will be the intensity. So we can say it like that. Coming to filtering techniques, we have been given some filters such as the box filter, cone filter, and the Gaussian filter. When it comes to the box filter, the intensity of the whole pixel is measured equally throughout the box. And the box filter is used in unweighted area sampling, where the filter is not ideal as it will make our image blurred. Coming to the cone filter, we have a pixel which is close to the center weight, and which center weight, which is the weight which is more than the other ones that are further away. And the filter used in weighted area the filter is used in weighted area sampling. So this is how the cone filter works. Coming to the third filter, that is the Gaussian filter. When it comes to the Gaussian filter, the Gauss function pixel closer to the center will weigh more. So this filter is better than the other two when it comes to filtering techniques. So Gaussian filter is considered superior to the box filter or the cone filter. So we in the example we can see that Gaussian filter is applied and the edge of the image is more smoother than the one with the box filter. So coming to the weighted pixel distribution. So what is it? The influence on the intensity of a pixel is determined by the weighting function. So the pixel which is right here located at the center, so its intensity is determined by the weighting function. So pixels which are cut through the center will have high intensity and will have more weight than one which is cut along the corner. Coming to pixel phasing, the position of a pixel is shifted by a fraction of a quarter, a 3/4 quarter, or a half of the pixel diameter by the electron beam. So this helps us to point closer to the true path of the object. So it removes the issues like staircase effect from our object. Coming to subpixel computation, subpixels are located near the center of the pixel area that are weighted more. It is more or less used in determining the overall pixel density. And as I said before, these are some of the examples of anti-aliasing images. So the image that is anti-aliased, or the image, so that's there's a difference. It's a more kind of smoother image which has more clarity. So thank you, friends. Thank you for your time, and thank you for this session. Thank you very much.